Welcome to part 2 of lecture 3 for Chemistry 418 Radiochemistry. This is the second part of the lecture on radioactive decay kinetics. Lecture 3 part 2 uses the same reading as the other part of lecture 3, Modern Nuclear Chemistry, chapter 3 and chapter 17.7, and Nuclear and Radiochemistry, chapters 4 and 5. This lecture, part 2, is going to cover equations. We're going to look at mixtures, equilibrium, and branching. We're also going to introduce an equation that we can use to calculate parent-daughter decays and decay chains. At the end of part 1 of this lecture, we went over some equations. Some of those examples included the decay of a single isotope. Now we're going to start this lecture talking about the decay of a mixture of isotopes. So let's talk about a composite decay where we have two unrelated isotopes. So the sum of all the decays are just thought of as the mixture of the two isotopes. So the two isotopes are acting independently. So the two radioactive species are mixed together. We can count the total activity as a function of time. Here's an example of what a curve might look like, and you can see that it's composed of two isotopes. So we can say that activity at any given time t is just equal to the activity of isotope 1 and the activity of isotope 2. That's equal to the decay constant of 1 times the number of atoms of 1 plus the decay constant of 2 times the number of atoms of 2. We can rearrange this equation where we have the activity at any time t is equal to the activity initial of isotope 1 times e to the minus lambda t, where lambda is the lambda for isotope 1, plus the initial activity of isotope 2 times e to the minus lambda 2 times t. We can take this equation and then solve this line for this equation. So we take this equation, put it into a solving program, generate the equation of the line, which is shown here. And then we also determine the terms of the components of this equation. So t is the x-axis, so we'll be able to solve for a1 naught, a2 naught, and lambda 1 and lambda 2. We run the equation. In this case, we solve for lambda 1 and lambda 2. These values are shown here. So the lambda is provided. We can get the half-life. We can get the initial number of the initial activity of isotope 2, and then the decay constant for isotope 1, the half-life of isotope 1, and the initial activity of isotope 1. We can also solve this graphically if we examine two parts. This is the longer-lived isotope. At the longer times, its decay dominates. You linearize on this semi-log figure. The longer-lived terms go back to the origin. You get around 2,000. So if I look at the value, 2,000 minus the total value would be equal to the shorter-lived isotope. So you could solve this graphically, or more directly, you can solve it with by just solving for the equation of the line that was generated. Then we can expand these equations into related decays, in other words, a parent and progeny, daughter decay. So we know that we have conditions where one isotope decays into the other, the decay series being the most common examples. So here's a figure that shows the uranium-238 decay chain, thorium, also the 232, and then the uranium-235 decay series. Those are the natural occurring decay series. However, you can pick out a number of isotopes that will often, particularly if they're far from the line of stability, they will also have decay chains. So as an example here, uranium-238 decays to thorium, eventually makes its way all the way down to stable lead-206. These of the three series. There are actually 4 series. One of them would start with something like Neptunium-237, which is short enough lived compared to the lifetime of Earth and the solar system that it will evolve decayed away. So for any system like this, for a parent-daughter decay, the rate of daughter formation is dependent upon the parent decay rate minus the daughter decay rate. And it's this relationship that we're going to really exploit to help understand the equations and how we can address relationships between parent and daughter decays. Let's consider a case where we just have one daughter that's being produced from the decay of one parent. So we have an isotope 1, and it decays into isotope 2. So the change of isotope 2 over a function of time is just equal to the decay of the parent that's going into the daughter, and then the decay of the daughter. So if we rearrange this equation, we get this term, we get this equation. So let's solve and substitute for N1 using N1 at times t is equal to N1 naught initial e to the minus lambda t. That equation then becomes what is seen here. Let's take a linear first order differential equation. This is let's just solve by integrating the factors to solve this linear first order differential. Let's multiply by e to the minus lambda 2t. The equation then becomes what we see here, where we get the change of n2 e to the lambda 2t is equal to lambda 1, the initial amount of isotope 1 e to the lambda 2 minus lambda 1t with respect to time. So we've gone through the equations. We now have this equation. Now let's integrate over time. So let's provide the integral, and we get this term. So let's integrate over what we see here, lambda 1, n1 naught e to the minus lambda 2 minus lambda 1 times t, divided by the difference between lambda 2 and lambda 1. From 0 to t, we get the equation becomes n2 e to the lambda 2 times t minus n1 initial is equal to a ratio of the decay constant for 1 divided by the difference between the decay constant for 2 minus 1 times this term n1 e to the lambda 2 minus lambda 1 times t minus 1. Multiply by e to the minus lambda 2 times t and solve for n2. Remember, we're talking about the daughter, so we're looking for n2. So n2 at any time t is equal to the decay constant of the parent divided by the decay constant of the daughter minus the decay constant of the parent. This talks about a ratio. This describes the relative growth and decay. So the decay of the parent is growing into the daughter, but as the daughter decays, it's disappearing. So you have the parent decay rate filling the daughter, and then the daughter decay rate having the daughter disappear. And the initial amount of the parent times e to the minus lambda 1 times t minus e to the minus lambda 2 times t plus any amount of the daughter that is originally present. So let's consider that term also. So now we have this relationship where we can use to provide an understanding of how much daughter is present at a given time t based upon an initial amount of parent and even an initial amount of daughter. So we have part of the equation which describes the growth of the daughter from the parent and then initial amount of daughter. So pretty straightforward. We have these two components that provide information related to the amount of the daughter available at any given time. Now, since we found n, the number of atoms, We can solve this equation for determining the activity of the daughter at any time by just by using the relationship between the number of atoms in activity. So activity equals lambda n. So we multiply this by lambda 2. So we take the term. Again, we have an initial amount of the parent, and now we have the daughter term. We can use this to find a maximum daughter activity based upon just change of the daughter with respect to time equal to 0. We're maximizing. And let's solve for t. We have the equation where the time that it takes to reach this maximum is equal to the natural log of the ratio of the decay constants divided by the difference of the decay constants. And that's not too surprising. We don't need to understand the amount of material that's available, parent or daughter. For it to reach a maximum amount of daughter, all it is a ratio and a difference of the decay constants of the parent and the daughter. So we can use this to derive an equation that's shown. We can use this equation, input data that says if I have a generator, for instance, I'm making technetium 99M, which is a 6-hour half-life from the decay of molybdenum 99. So this is the parent. This is the daughter. Find the time for the maximum daughter activity. Well, we just plug in the lambda 2, which is the technetium. Lambda 1 is the molybdenum. We make sure the units are the same, days and hours. So make sure you convert this hours into days. And this basically says in about a day, this has reached a maximum. And this is actually a useful consideration, useful term. If technetium 99M is a workhorse for radiopharmaceuticals, it's sent to medical centers as molybdenum 99 on a generator. That generator, the molybdenum decays into technetium 99M. The molybdenum is decaying with a 2.75 day half-life. Technetium is a half-life of 6 hours. So this basically says you can separate the technetium from the molybdenum, wait another day, and you'll have reached a maximum amount of technetium you're going to get from that generator. In the previous slide, we used a differential to evaluate conditions where the maximum amount of daughter would be created from the decay of a parent. We can actually make some more simple relationships based upon the relative differences between the decay constant of the parent and the decay constant of the daughter, or the half-life relationships, right? So in other words, there are relationships where if the half-life of the parent is much longer than the half-life of the daughter, you can simplify some of the equations. So let's take a few conditions. For instance, the simplest one would be that there's no daughter decay. The number of daughter atoms is just due to the decay of the parent. So the daughter atoms keep growing and the parent value keeps decreasing. So this is where if I had an isotope that was decaying directly into a stable daughter, that would be the case. And let's say if the daughter is radioactive, there's a few different cases where there's no equilibrium. And equilibrium means that eventually the relationship between the decay of the parent and the decay of the daughter would be established. If the parent is shorter lived than the daughter, or if the decay constant of the parent is much larger than the daughter, no equilibrium is attained. The daughter reaches a maximum activity when this condition is solved. But imagine you have a condition where the parent has a half-life of a second and the daughter has a half-life of a year. So within 10 seconds, all the parents decay and all those atoms are now daughter atoms where its half-life is a year. So within a year, half those daughter atoms will decay. So initially, you'll get this burst of parent activity, then decay will be solely based upon the decay of the daughter. Another relationship is where the parent half-life is greater than the daughter half-life. And we'll see that there's actually two types of relationships that we can describe this way. One is transient equilibrium. In this case, where the parent half-life is about 10 times of that of the daughter half-life. One of the other properties is that because I guess the difference is relatively small, the parent half-life may decay, may show changes during the measurement process. So this is called transient equilibrium, so that there's a change that's ongoing. The parent half-life is short enough so that the activity of the parent changes over time. Now the decay constant of the daughter is going to be greater than the decay constant of the parent. The ratio between the parent-daughter becomes constant over time. As we see, as shown here, here's a total activity. There's a activity of the parent. There's a daughter activity that grows in, and it becomes constant with that ratio becomes constant over time. Now, this ratio is going to be the same. The total value will change. And so we see that this ratio is going to be constant. And as t goes to infinity, we get, as this goes towards infinity, this goes towards 0. And we can collapse the equation so that the number of daughter is approximately equal to the decay constant of the parent divided by the difference between the decay constant of the daughter and the decay constant of the parent times the initial amount of the parent e to the minus lambda t, so the decay rate of the parent. It becomes this equation, and then we can just look at a ratio. This constant ratio is shown here, where it's just really this term is the ratio that is defining the ratio. So the ratio between the number of daughter atoms and the number of parent atoms at equilibrium is equal to a ratio of the parent decay constant minus the difference between the daughter and the parent decay constant. Now, imagine we have a condition where the parent is much, much longer lived than the daughter, and generally what this means is that over an observed time frame, the parent activity doesn't change. So imagine you're measuring something that has a half-life of 1,000 years, 10,000 years, and you're measuring it for 100 hours. You're not going to see the amount of change that is going to occur in that parent won't be observable, but the daughter will grow in. So you may have an amount of parent, B shown here, the daughter grows in, and then the total activity is basically twice the parent activity. So in this case, the parent does not measurably decrease in many daughter half-lives. We see that that seems to be the case. And then we have this relationship. We just took this relationship from the from the transient equilibrium, and lambda 2 minus lambda 1. Lambda 1 is a very small number. It's fundamentally just equal to lambda 2. So we get these relationships where n, the number of daughter atoms divided by the number of parent atoms, is just equal to a ratio of the decay constants. And we actually see that what we get over time is that the activities of the two become constant. Because if I were to take this equation, n1 lambda 1 is equal to n2 lambda 2. So this equation, our transient equilibrium, since this value is small, we basically eliminate it from the equation for the secular equilibrium. And then we get these conditions, and the key condition being that the activity of the daughter winds up being equal to the activity of the parent. So we talked about a parent-daughter decay. Well, what if we have a condition of many decays? So parent, one progeny to the next, so daughter, granddaughter, great-granddaughter. In that case, let's take the example of the third, so the granddaughter. Well, that's the change in the granddaughter with respect to time is just equal to the decay of the daughter that's populating the granddaughter minus the decay of the granddaughter. And we use the Bateman solution to calculate this entire chain. And the equation for the Bateman solution is shown here. It assumes that only parent is present at time 0, and we have a factor where this C1, C2, Cn factor, so whatever n is, the n is equal, can be 3, 4, 5, or 6. It's equal to this factor here, which is shown as the decay constants from 1 to n minus 1, and the difference between the decay constants of 2 minus 1, of 3 minus 1. So of all of them for this n value, for this subscript value, all the decay constants minus that value, time the initial amount of the parent. This C2 value, and again we've got C2 e to the minus lambda 2, so that's the daughter decay constant. Well, that's just equal to, again, the same factors here, all the decay constants to n minus 1. So depending upon what your n value is here. And then the decay constant of 1 minus 2, decay constant of 3 minus 2. Right, so now we've taken what we're subtracting the decay constant by is the coefficient or the factor of this C value. It goes on and on. So you can build many, many chains. As you can imagine, writing this yourself, there's a lot to take into account, and it's a matter of often if I were to assign this as a homework problem, it becomes a homework problem in making sure that the program was written correctly. Another way to do this is to get a Bateman solver. There's Bateman solvers available, and one is at this website that's listed here. And if we go to this website, you'll see a page. Click here to download the program. It'll ask you for some information, and then you can download the program. This version, there's also a link on the Canvas site, but this version is version 1.0.0.1. We also have version 2.0.0.2 available from the lecture link. So if you go to the lecture link, you could look at both programs. You can read the information that's available. They are looking for feedback, so they'd be happy to have feedback. And this is a PC program. So if you have a Mac, if you have an Apple product, it does not run on an Apple product. We're going to use the ERG version 1.0.0.1 to evaluate a parent-daughter, granddaughter decay series. Let's use a complicated example so that it shows that this program is pretty useful. We select the element, and then we select the mass. So let's take uranium-238. When you select a given isotope, the decay series shows up, and we see that uranium is at the top of this decay series. We have the half-life of the uranium, and this is an activity that's selected for the uranium. Let's click on the box, and we can change that activity. Let's just call it 1,000,000 becquerel. A source term means that the activity is constant. Fundamentally, for this example, the uranium-238 will be constant because the half-life is 4.5 billion years. All right, and we see the decay scheme. It goes down to thorium. And if you click on the box, and I wanted to have a system where some of the daughter was also initially available, we could add that information too. So if I want to put 1,000,000 becquerel thorium-234, I could do so. This isotope here, the protactinium, it's metastable state. It has a branching. So the thorium decays, 234 decays to this protactinium, 234. It has a branch between the protactinium ground state and this uranium-234. See that most of it, 99.84%, goes to the uranium state. We can also see here the half-life of one of the daughters, the uranium. That's 245,000 years. So this does tell us if we want to see some growth of the daughters, we need to have the calculation run for a few multiples of 250,000 years. And we can follow the decay chain. We see that radium's involved, radon, number of isotopes with lots of branching ratios. So for instance, this polonium to the astatine, very small branching ratio, very small branching ratio of astatine to radon. We wouldn't expect this to be important in this decay chain, but the program will calculate it. Then it goes all the way down to stable lead 206. So we can now look at our decay chain. Let's put in our parameters where we could either select atoms or activity. So start with the number of atoms of uranium or activity. Let's stick with activity, 1,000,000 becquerels. We can actually change that unit. It wouldn't change things in terms of the values, just the units. And now this is important, the time constants. We said we want at least, 1,000,000 or so years of calculations. So our time is going to be years. We could do anything from microseconds to years. Each step of time we're going to say is 10,000 years. And let's do 500 steps. And 500 is the maximum number of steps we can do. This means that we'll go for 5,000,000 years. Okay, let's calculate the decay. It's calculating. Let's look at the results. One of the results is shown here, where we have the decay of uranium. This red line doesn't change much. And now here's the decay of the daughters. So the thorium, protactinium, this is uranium 232. A lot of these are going to be coming in at the same. The thorium 230, and then the radium 226. Admittedly, we don't have, and these down here, these are very low because their branching ratios are very, very low. Basically, this shows that we get to equilibrium in about 2,000,000 years for uranium 238. So the equilibrium, this is important to remember, this is a good demonstration. Equilibrium is not dependent upon the parent, it's dependent upon the daughter. Right, so this information is available, but it's kind of a little difficult to really get details. One way of getting the details on the information is to look at the decay results, and you can actually calculate the values of the decay results. So this is the time. Remember we said each time constant that's going to be calculated was 10,000 years. We did that 500 times, so we eventually go up to 5,000,000. We have the activity. We start off with 1,000,000 becquerel. We see that uranium does decay a little bit, but not much. 99.9% of the uranium is still there, of the uranium 238 after 5,000,000 years. And now the other isotopes are all available, and we can see, for instance, if we pulled up the radium 226. Now, one thing with this program I want to note that you get an initial value, which is spurious, right? At time 0, we defined everything as 0. Some of the isotopes have calculated very small values, very small activities, even minus activities. Those should be ignored. Okay, so what we can do, we could look at this value, and we can see when the parent and the daughter's value starts to become equal, so we get an idea of when equilibrium is reached. Better yet, we can export this to a CSV file so one can analyze it on Excel. So again, if you wanted to, you could take this data, go to export table, export it, and then you would have data available. Again, you can change the activity units or you can have the number of atoms as a parameter. So you can change some of the conditions, and you can select any isotopes that you're interested in for using this version 1.001. We'll use the other ERG program, version 2.002, which is copyright from 2012, to provide an example of just the decay of atoms as opposed to activity. So let's pick an isotope to start with. Let's select zirconium-95. So we select the element, then we select the isotope, zirconium-95, niobium-95, molybdenum-95, beta, 2 betas, and a stable molybdenum-95. The input data isn't done by clicking on this bar. It's done through the table. So let's just say there's 100 atoms of zirconium, fundamentally a percentage. And let's also include the molybdenum into the output since we're talking about atoms. Let's click on the parameters, pull up the parameters. Let's go for 200 days, shown here. The half-life is 64 days, 34 days, and stable. So we should see some growth and decay in this period. Select that. Let's calculate it. Here comes the graph. And sure enough, we see that zirconium decays, the niobium reaches a maximum, then starts to decay, and the molybdenum does nothing but increase since it's stable. We can select this bar. If I move this around, I get the day and the amount of the zirconium, niobium, molybdenum. I can see that the niobium, I can see where it kind of reaches a maximum, then where it starts going down, and I can quantify that. Just like the other program, I can evaluate the data. So here's an example of the amount of atoms as a function of time. Obviously, this value should be 0, but we go through and we can see that zirconium does nothing but decrease. Molybdenum goes up, reaches a maximum, then starts decreasing, and molybdenum just increases. It does not decay. And just like the other program, we can export the data. I can export it as a CSV file. There's also some data libraries. I can look at the emissions, the alpha. I can select an isotope alpha, beta, and the gamma emissions for the isotope. I can select niobium-95, look at its emissions, no alphas, 3 beta energies, 3 gamma energies. I get the energies and the decay probabilities. I can also look up atom, if I just have a gamma decay, I can write in, for instance, a gamma decay, 661.6 keV. I can do a tolerance of 0.1 keV, so it'll be 661.5 to 661.7. It pulls up all these values. So if I was interested in, if I just saw a gamma line, for instance, cesium-137, that's the gamma that I'm thinking of, I can get that gamma and also its decay probability. So this program, you could use this program, you can use the ERG 1.001. Either will work for looking at growth and decay, series, daughters, decay chains. You can get data out of both. If there's any assignments, these will be used on, they'll operate on PCs, they won't operate on Macintosh. And if you have an issue with that, we can resolve that through the course. One of the terms we discussed in the example of the uranium-238 decay is branching decay. And this showed a condition where an isotope will decay by 2 different routes. Alpha and beta was the example that was shown in that decay. Now, if you look up an isotope on the chart of the nuclides, you're only going to find 1 half-life. So an isotope only has 1 half-life, therefore it only has 1 decay constant. But actually what that decay constant is, it's fundamentally a sum of all the decay constants. However, often only 1 decay constant dominates. It's fundamentally equal to the observed decay constant, so that observed That half-life is the observed half-life. If something has a very low probability, it has a large half-life, and it often isn't observed or difficult to observe. So for a branching ratio, you could actually calculate partial half-lives or partial decay constants. From this equation here, the sum of any decay constant is just equal to the sum of its components. And let's take an example of an isotope that decays by alpha and beta. So the alpha decay constant and the beta decay constant is equal to the total constant. The branching ratio is just the ratio of the decay constant of the alpha divided by the total decay constant. You could also look at the half-lives, where the branching ratio is the total half-life divided by the half-life of the decay route. So in this case, you'll observe that since it's a number less than 1, the half-life of the decay routes are less than the half-life that is provided in the observed half-life that's provided in the chart of the nuclides. So let's consider an example, bismuth 212. What's the half-life for each decay mode that decays by alpha and beta? We see that there's a 36% alpha branch, 64% beta branch. The decay constant's the half-life's about a minute. So log 2 divided by 60.55, the decay constant's about an hour. The half-life's about an hour. The decay constant is log 2 divided by 60.55 minutes. We see that the branching ratio is equal to, for the alpha, 0.36 is equal to the alpha decay constant divided by the total decay constant. Let's solve for the alpha decay constant. As shown here, we get a decay constant of 0.0041 inverse minutes. Log 2 divided by the half-life is equal to the decay constant. We use that to calculate the alpha decay, which is about 170 minutes. The alpha decay half-life. We do the same thing for the beta decay. We see that its value is about 95 minutes. We could calculate the half-life directly using this ratio. If I know that the half-life total is 60 minutes, the alpha half-life is equal to the total half-life divided by the branching ratio. Same thing for the beta, total half-life divided by the branching ratio. So in this way, if you're given a total half-life and a partial decay constant or partial half-life, you can calculate the branching ratio, or you can calculate the decay constants and the half-lives from the branching ratio. One of the utilities of all these equations is something that's shown here. This is an example of some dose from radioactive waste as a function of time. The dose is related to the activity. This is something that I worked with when I was a postdoc in Germany. It showed dose as a function of time for the yearly activities dose per person in persons as a function of years. And this is from radioactive waste that was burned up at 33 gigawatt days per ton and without reprocessing. But what it shows, this is all broken up into elements. It could be broken up into isotopes, but you see some behavior such as the growth of the americium, the decay of the americium. Neptunium grows in and then decays away. This has to do with the growth of one isotope into another. Uranium has a decay here, then another decay here. Those has to do with the half-lives of the uranium, and then something like iodine, technetium. Single isotopes, long-lived, tend to be fairly constant and then decay off. But these equations and these parent-daughter relationships that we just went over can be used and are used to understand the long-term behavior of isotopes in any environment. This concludes Lecture 3, Part 2 of Radioactive Decay Kinetics. When you've completed this lecture, please continue on to Part 3.